Hello everyone. Today I will show the solutions to the Prairie Math League High School round 132, problems 5 and 6. For problem number 5, we have a sequence which has the first two numbers and a recurrence relation. And we're asked to find the 223rd term. Now we can just list the first few terms, which is generally a good idea when dealing with these kind of problems. So we have 2, 3, 3 over 2, 1 over 2, 1 over 3, 2 over 3, 2, 3, etc. Now notice here, this part and this part is the same. So it's going to, after this point, it's going to repeat. And since this has length 6, it's going to repeat every cycle of 6. So this sequence has order 6 in other words. Now, 2023 is one more than a multiple of 6 because 2022 is a multiple of 6. So since 2023 is congruent to 1 mod 6, we have that a of 2023, a sub 2023 is equal to a sub 1. And a sub 1 is 2. So the answer is D. Now for problem number 6, we're given a square root of 2 by 1 rectangle. So, like this. Then we rotate it around its diagonal. And, so this rectangle is rotated around this diagonal, and we get a shape that looks something like this. So this is what this diagram looks like. Now, we can take a 2D cross-section, as in this diagram here. Except that we don't need this part, because it's unnecessary. We only need to focus on one half of it. And now we start doing a bunch of similar triangle chasing, angle chasing, etc. So it gets a lot harder here, but whoops. We label this as A, B, C. So these are vertices of the rectangle. D is the rotated the point where the same rectangle rotates a full 180 degrees about the diagonal. And so this is a reflection of this point. This point. Now we set this to be x. And first of all, notice that AD prime x and CBX are identical because of symmetry. Now we can draw perpendicular from x to M and draw perpendicular from B to E. Now notice, again by symmetry, this angle and this angle are the same. We also have 90-degree angles. So we have a whole bunch of similar triangles that we can now access. AMX is similar to AEB, which is similar to BEC, and this is similar to ABC. There are more similar triangles in this diagram, but they're not really necessary. Now we can find a bunch of side lengths here. So, we see that AC is just square root of 3 because it's AB is 1, AB is square root of 2 and BC is 1. So, we just have the Pythagorean theorem. Now, as we mentioned before, we have symmetry here. So AM is equal to MC. So this is equal to this. And hence AM is equal to AC over 2, which is equal to square root of 3 over 2. Now we're going to start using our similar triangles here. So BE is equal to AB over AC times BC, which is equal to square root of 2 over square root of 3 times 1, which is square root of 3. Or square root of 6 over 3. And using a similar argument, but instead of multiplying by BC, we can multiply by AB to get the side length of AE to be 2 square root of 3 over 3. And finally, CE is just AC minus AE. So it's this minus this. And we get square root of 3 over 3. Now we have pretty much all our side lengths required to solve the problem. So the last part requires a bit of 3D geometry. So if we go back up to this diagram, notice that we can just get the area of this part here, or actually more accurately this part. We don't need, we can multiply by 2 to get this part later on. But anyways, this basically becomes, we can basically split everything into 3 volumes. This one here is the yellow volume. This one here is the blue volume. And this one here is the pink volume. Now, as we said before, we want to find the bottom half, so we only need the yellow and blue volumes. So first we start finding the yellow volume. This is just a cone with radius BE and height EC. Now EC we know from here, and EB we know from here. So we can just get the volume of the cone using BE as the radius. And we get this expression here, which you can evaluate on a calculator or something, but we need the exact value, so it's better not to evaluate by a calculator. So now for the other area, this area is trickier. We need to actually use complementary counting here, or something like that. 3D geometry version of complementary counting, where we basically find the area of this large cone, which consists of both the pink and blue cones, then subtract the pink cone. Now we can find each of these cones' volumes, or we could also be a bit more clever and note that AM is equal to 3/4 of AE. Now look, this is true because AM is square root of 3 over 2, AE is 2 square root of 3 over 3, and yeah, you can do the rest of it to find that AM divided by AE is 3 over 4. Now, what's nice about this is that it allows us to we only need to compute one of these volumes. We're going to compute this one here. Then we subtract 3/4 of that volume. Not 3/4 actually. Notice here again that this is a side. So we need to subtract 3/4 cubed over here. So this volume is just 3 over 4 cubed that of this volume. So this simply factors out to here, this expression, and we can get the area of cone, the volume of cone of the pink and blue cone to be as with BE the radius again, and this time AE is the height, and we get this expression here. Now all we need to do is sum these two expressions to get this volume, then multiply by 2 to get this volume, this entire answer volume. Now I'm not going to go over the rough work here, but we eventually should get 23 square root of 3 over 72. Now notice that this problem asks for A plus B plus C in this form. Oh wait, I forgot a pi here. Sorry. But anyways, now we find A plus B plus C to be 98, which is option A. Thank you for watching.